Perhaps we can begin and then some people will join in as usual. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. We are delighted to have Andrea Tesi from Florence, and he's going to talk about exploring ultra-high energy neutrinos with transport equations. And maybe I'll send you a reminder when 5 minutes are left, approximately 45 minutes or so.
Okay. Thank you very much, Anish, for the invitation. I see that many of the authors of this paper, actually half of the audience is made up of authors of this paper. So I think I can really talk informally about this project. So this project started with the hope of chasing the KM3-net anomaly. And it's a working collaboration with people in Florence. And let me especially mention Stefano Palmisano and Michele Tammaro, who are postdocs at the GGI. So we started with the hope of chasing the anomaly, but then we understood that it's very difficult to reconcile the anomalous, let's say the ultra-high energy event of KM3-net with what is known of other high energy events, for example, from IceCube. So the idea of this talk is to go through a little bit the assumptions in the standard model that leads to the prediction for ultra-high energy neutrino events. And the outline of the talk is the following. So I will very, very quickly introduce the topic, then I will just comment on how our derivation of observables relevant for the neutrino telescopes, with an emphasis on the standard model systematics and inputs. Then I will just present our computations and comparison with data. So we perform fit both to IceCube and KM3-net. I will comment on the results of these feeds, and then I will just make a few comments and outlook. So I think, so I'm no expert at all on neutrino physics, and even less on neutrino telescopes or neutrino detectors. But what I learned doing this project is that neutrino telescopes are not really neutrino telescopes, but they are muon telescopes. So they are really muon detectors. And up to now, there are two. One which is super well known and established, which is IceCube. So the figure on the left, which is located at the South Pole with a hard volume of 1 kilometer cube and with a time exposure of more than 10 years. While on the right of this slide, we have KM3-net. This is a picture. I don't know if this is the French or Italian site. So KM3-net, for what we are after, especially so the Italian site, so the ARCA module has been taking data for less than 1 year up to the announcement, with a hard volume of 0.15 kilometer cube. Now, this picture already shows why maybe KM3-net is not fully at the design volume, because it's very difficult to put these optical modules in the deep sea. So probably IceCube is easier. It's easier to drill than just to emission to install these modules for KM3-net. But the hope is that within this decade, KM3-net can reach the full design volume. How do they work? Well, very roughly, they are detectors, but also targets. So they detect radiation from muons, and they also produce muon through possibly the scattering of neutrinos, of nucleons in the ice or in the sea. Okay. Now I put a star here in the word targets because I mean, as it will become apparent very soon, muons coming from neutrinos can be produced away from the detector. Okay. So they are targets, but you know, you have an even bigger target, which is the Earth. Okay. So what is the anomalous, or let's say not anomalous, it's an event, they measure it. So it's an ultra high energy neutrino with reconstructed energy of around 200 PV. You see it in this plot with the big blue cross. Now this plot shows the reconstructed neutrino flux as a function of neutrino energy. But what, again, is really measuring the detector is muon energy, and possibly also muon direction. As you see, the measured muon energy is around 120 PeV with a big error, and with an angle which is determined experimentally to be within the frame of the experiment, almost horizontal. So it comes from the Isle of Malta through the sea until it reaches the detector on the Sicilian shores. Okay. Now, as you see from this plot, there is also visibly some tension between the previous measurements from IceCube at lower energies, so reconstructed lower energies of neutrinos, and yeah. Even from this plot, if you look at the predictions from IceCube, you might say there is already some 2 sigma tension, and we are going to assess the tension between IceCube and KM3net under the assumption of a Gaussian model later on. So it's very tempting to speculate about new physics generating this event. So there have been works in the literature, but for us it was more interesting maybe to reconsider the full derivation of what connects really the number of muons detected inside the detector and the unknown input of neutrino flux at the surface of Earth. So we wanted to do first principle computation, aiming at deriving the experimental rate. So for today, I will try to be an experimentalist in the sense that I want really to go to what the detector measures, starting from first principle. So what they are really after is the number of muons per time, per energy, and per direction, so solid angle, as a function of the only unknown, which is the neutrino flux at the surface of Earth, which is possibly a function of a neutrino energy and direction. So the right tool to address this question, so to arrive at the observable, is to fully derive the transport from the surface of Earth to the detector by following the muon distribution. So muons are created along the tracks that goes from the surface to the detector, possibly, and we want to track this f mu, which is the full phase-space distribution of muons as a function of time, position, and momenta. Knowing this function, f mu, which is our target today, we can just ask whatever we like. For example, the number of muons per time, even more differential measurements like the number of muons per energy. So as soon as we have f mu, we can compute all the observables, like sampling this distribution with proper weights. Let me also know that let me also tell you that we just restrict ourselves to standard model. So into the computation of f mu only goes the knowledge of the Earth density, for example, and all the standard model processes that contribute to the production of muon, starting from an initial flux of neutrinos. Okay, so this is what we want to do today. So I mean, very basically, we didn't know we didn't know much at the start. We know little at the end. So the right tool to describe the evolution of the muon distribution is a transport equation. So we want to really, solve this equation, which tells us the distribution of muons in time, position, and space, when sourced by source term, which here I call K. So this is a kernel containing all the interaction that contribute to the change of distribution. So there are just a few in the standard model. So we have charge neutral current interactions that contribute to production and losses of muons, muon decay eventually. Then QED processes that contribute to the energy loss of muons. And if the neutrino flux is democratic, maybe a tau neutrino can produce a tau, and the tau can decay to muon. And we also try to follow this population of muons from tau decays. Now, with the hope of comparing with the experiment, we want to retain fully differential information in the muon kinematic, especially muon energy and direction. And as you well know, this equation is in principle non-linear. So, I mean, it can be difficult to solve it unless you make some approximation which are, sensible. So inside K, there are processes that are rare and processes that are not so rare. Let's say they are fast and slow on the time scale of propagation. So, for example, a very effective way to follow this is to realize that energy losses of muons are very fast on the scale of propagation, so they can be integrated out sort of and plugged into the evolution of the energy of the muon along the line of propagation. So here you see that the p dot of the muon, which is essentially, I mean, you make a change of variable, is the energy loss per propagation, as the typical expression of the in the x equal to polynomial in the energy. So as soon as you know the coefficient A and B, you can follow the energy loss, and then you remove it from the kernel. Okay. We also remove very rare muon interaction, like disappearance from charge current or decay. Okay, they are slow. We are not, making a big error neglecting them. So eventually, K only contains production of muons, which are rare but not so rare, not so slow. Okay, so with this approximation now, kappa doesn't depend on F mu. So the equation, okay, is a differential equation, but it's linear, so you can solve it with an integral. Okay. So we retain two terms inside the kernel. Charge current scattering of muon neutrinos of nuclei. So the first term, fully differential in the neutrino cross section. Okay, sampled by the distribution of muon neutrino inside Earth, which we also need to know to compute this kernel. And tau decay, which is again an integral over the full distribution of tau inside Earth times the differential decay rate. Okay, and so the equation is simplifies because now everything is a function just of the momentum of the muon. Okay, and we can just solve it with the standard procedure of integrating along the line of sight. Now, as you see, the kernel depends on neutrino flavor and tau distributions, but under the assumption of that I outlined so far, I think the system of equation that connects neutrinos, taus to muons is factorized. So, I mean, it's complicated, but in principle, one can solve it prior to the computation of the muon production in this approximation. So again, as you know, there are flavor-independent contribution to the evolution of neutrino propagation inside Earth. And then, of course, if you include tau, you have flavor-dependent effects into the equation. So in principle, one needs to solve this system, but we will make some approximation. But the important thing for us is that this is factorized. So I mean, if we extract it from other works, we can plug it in our form. Okay. Now, So this is the differential equation, and we how do we solve it? We solve it along the line of sight. So we physically, so a neutrino comes in the Earth, it can convert to muon randomly in any position. Then this muon travels towards the detector, so in a region where we want to know the muon distribution, losing energy, okay, in traveling in space. So the full solution is reconstructed like you do it in cosmology for the CMB by solving this differential equation. Especially the most important is the one that tracks the energy loss of the muons, which here is a bit implicit in this, but it depends on the position. So in principle, it depends on the density of Earth at a given location. Okay, so if one knows the full 3D, density profile of the Earth, this can be complicated at will, but still is just an integral. Okay, just an integral because we assume that the muon direction is not evolving along the line of sight, which makes sense for the energies that we have in mind. So there is a overall scale in the system, which is the length of the path traveled by a neutrino muon coming from the surface to the detector. Okay, so later on I will tell you the numbers for the two experiments. Okay, so it's I mean, we didn't know, so we were surprised by the probably an obvious result, which I think is obvious. So the fully differential muon distribution is just this function. Okay, so we can compute it for trial expression of B and location and position of the detector compared to the impinging direction and entrance of the neutrino on the surface. We also need to physically integrate overall the possible conversion point. So this variable C is a length, and we integrate over the possible muon production location. Now, as you see, again, there are analogies with other type of similar calculation. Here we have an exponential cutoff, which is a range dictated by how much energy you lose per kilometer. And indeed, we are just restricting eventually ourselves to compute this muon differential distribution, just taking into account muon produced not so far from the detector. Interesting, however, they can be produced they can be produced as distant as a few units of the detector size. Especially let me just go ahead. So the event measured by ChemTreeNet, and they are pretty sure that it was produced outside the detector. So we don't know where, but for sure outside the detector. So this explains in formulas, if you want, that the effective volume of this neutrino telescope is much bigger than the hard volume. If 1 over b, which is the distance over which the muon lose order 1 energy, is sizable. Okay. Now, another way to present the result, which is slightly, we find it slightly more general, but probably, similar to what people usually do, is to compute as in cosmology the transport function, sorry, which transport a neutrino of given energy to a muon of different energy measured at the detector. And as you see, this function can be complicated, but it is only standard model dependent and environmental dependent. So we can, in principle, compute once for all if we have, full knowledge of what goes inside this function. Of course, this function is reminiscent of the kernels that they contribute to muon production. So you have two types of transport, which depend on flavor. So the first one is as you see here in the first line, is the transport function from muon neutrino to muons. And the other, which is slightly more complicated, it takes couple of more integrals, is the function that goes from mu tau to muons. Of course, going from tau neutrinos, you have to go to a tau, then the tau has to decay. And as you see, there are a few quantities here that are important. The number density of nucleon inside Earth as a function of position, the differential rates, fully differential in the muon momentum, as well as D, which is the neutrino transparency. So that will take into account the solution of neutrino propagation, which is important to know what is the conversion probability from neutrino to mu at a given position. So schematically, you have this type of connections going from the left, from the neutrino at the surface of Earth to the detector. So depending on the flavor, muon or tau neutrinos, you can go directly to muons, or you have an intermediate step. And there are a few time scales that are important. As you see, the line that goes through the tau is a bit more complicated. There are more scales. So here we expect the biggest deviation from the so-called effective area calculation, but also probably not so relevant for the anomalous event of Kentri-Net. There are also hierarchies of scales in this problem. So here you see the Earth, let's say half of the Earth, and the green is where is Kentri-Net or ice cube, and so you see that muons can be produced everywhere, but only the muons produced in an effective radius 1 over b are the one that you can really hope to measure in the detector, in ice cube or Kentri-Net. And they can come both directly from conversion of muon neutrino to muons, or maybe with an intermediate step. So you created somewhere a tau, so in the purple, sorry, I'm colorblind, so but in the purple stripe, and then the tau can decay, so it travels, it's long-lived, this energy travels, and then maybe it decays close to the detector, and the muon can be recorded. The typical size of 1 over b of the muons is 3 kilometers, which is, is a linear distance bigger than the size of the detector. So you increase effectively the number of muons. So the target is actually slightly bigger than the art volume of the detector. So from this point of view, maybe even, it's not surprising that Kentri-Net have seen something despite having just a few optical modules active, okay? Because it was produced, it doesn't matter so the active volume for the production. They can come from a bigger volume. You also see that for the energies that are relevant for the discussion, instead the effective length scale of tau energy losses is slightly comparable to its decay length. So here there is not a clear separation of scale, so one has to do a numerical calculation which to assess the importance of taus. Maybe we will do it better in a future work. Now, what are the inputs? So I'm mumbling about standard model inputs and environmental inputs. I've been mumbling for the last 20 minutes. So the biggest, source of uncertainty are neutrinos from two types of effects. One is the knowledge of neutrino cross sections at high energies, and the other is the fact that we don't know the neutrino flux at the Earth's location. But this is actually, what you want to infer. So it's the model part of the discussion. We want to infer the neutrino flux at Earth's location. Then I already mentioned the propagation of charged particle and the density of Earth, which we took to be equal to the Prem model. so preliminary reference Earth model, something like that, I think is the spelling, which is just approximating the Earth as shells of constant densities. So neutrino interactions, neutrino interactions, at this energy you expect the energy to saturate, because the center of mass energies of these interactions are well above the electroweak scale. Sorry, the Mandelstam S of this process is in the ballpark of 10 TeVs, if I recall. So you are in a regime where you are at really high energies, and in this regime there is a bit of uncertainty on the effective dependence of the total cross-section on the neutrino energies. I think this is a very old result, in the sense that people quote this type of uncertainty at the energy that are relevant, so hundreds of PV, in the total charge current interaction of neutrinos. And this for us is a potential source of uncertainty, but eventually we present most of our results aligned with the best fit of this expression. So the problem here comes from the fact that these high energy neutrino events they cover a region of kinematic which is not well under control from the point of view of the knowledge of the PDF that you need to compute this type of scattering that you see here in the inset. So a pragmatic approach that I've seen in many papers is to parameterize the total neutrino cross-section as a constant term, which is at the reference of 10 PV, 10 to the minus 33 centimeters square, with a modulated dependence of on the neutrino and the incoming neutrino energy, modulated with an exponent lambda which is smaller than 1, so 0.3 something. So eventually maybe it's just a log. That is what probably you expect at extremely high energy for the general behavior of total cross-sections. Okay, another important aspect for us that goes into really the calculation of the transport is the inelasticity distribution of the muon, the outgoing muon from the neutrino scattering. So that can be computed with tools, and here you see P of y, which is, sorry, look at the right. So P of y is the distribution, the differential distribution of the cross-section as a function of the inelasticity, so this type of distribution. So you see that the average is that the scattering is slightly inelastic in the muon energy. Okay, so this is what goes into our computation. And then there is a neutrino propagation, which again is sensitive to the value of the cross-section, and okay, can be taken into account. This is just a fact that it's mostly just an exponential. It can be computed this way using water equivalent distance, which is what usually is important for the attenuation of neutrino going through the Earth. And okay, in principle, since the mean free path in water equivalent kilometer is a function itself of the cross-section, one can maybe refine the analysis, including nuisance systematic uncertainty into this attenuation, transparency, or neutrino attenuation as well. Okay. What about the neutrino flux? The neutrino flux is usually okay. So the neutrino flux is unknown, but there have been data at lower energies than K3net event. So there is an expectation that what will drive the tension between the two experiments. So in principle, is a function of energy and direction. We assume that these dependencies are factorized. So there is an amplitude, which is F nu at the Earth as a function of energy, times a directionality component. Usually, you see that the normalization of this flux is like taken at this E star. E star is usually 100 TeV, if I recall. At 100 TeV, you have this expectation for the flux. Okay, and usually people were fitting ice cube with a power law. Okay, so but in principle, one can add an energy localization effect if the power law fit will not make compatible K3net and ice cube. And then there is the direction. So the direction maybe is just a constant in the case of diffuse neutrino flux, while in the case of a point source, omega nu will track the position of the source as a function of time when during the day. Okay, so there will be clear impact of the reconstructed direction of the hypothetical source. Okay, so we consider combination of these two possibilities, both power law and localized energy spectra, both diffuse and point source. Okay, then eventually we compute this, so which is again the full formula, and it is important to take, so this formula is fully differential, especially in the direction of muons. So we can average over the direction, over the full sky, or over the full day in the case of diffuse and point source. Okay, good. So if you want a decomposition of the contribution to this formula, this is what matters. So there is the effective area of the detector, the local density near the detector in the shell of order 1/b, neutrino cross-section evaluated at typical energy, the reconstructed of the muons, the flux, this exponential, which is the neutrino attenuation, and then interestingly, there is this linear distance, which is the sum of the detector size plus this effective length that collects all the muons produced away from the detector. So there is an enhancement. We include effective volume. So eventually, the number of events depends on a volume, but this is not the volume of the region where there are the optical modules. Okay, so there are similar expressions for tau neutrinos, but they are more complicated, less factorized. And anyway, when doing the fits, we use the numerical integration of the transport functions. Okay, let's go to data. Now, clearly, even from the plot of the K3net collaboration, this event is an outlier. So, given what we know about, the fit to diffuse power spectra, to the diffuse power law spectra from ice cube, you didn't expect this event. Okay, this is really a zeroth order statement. Okay, but since we have the observable, so we connect the flux to what is really measuring the detector, we can even ourselves try to do a fit. Okay, taking for example, all the events collected by ice cube, including possibly a model for the atmospheric contribution of neutrinos. So we subtracting what you don't want. So you don't want to have high energy muons that comes from atmospheric neutrinos. You want to remove them. Okay. Now, the problem is then how to compare data sets, because we cannot tell that just two data are incompatible. So you need a model to say this. So, for example, a first question is, will be ice cube and K3net compatible assuming a power law spectrum, compatible assuming energy localized, compatible assuming a point source? So to estimate the compatibility between, or the tension, if you want, between ice cube and K3net, we use this procedure of computing integrals, if you want, of the likelihood, so the so-called bias factor. Now, bias factor are defined with the same data. So what we do is the following. We use the correct definition of bias factor because we want to compare dataset 1 and 2, say ChemTreeNet and IceCube, or IceCube and ChemTreeNet, by computing the evidence given the data, given the dataset 2 for a given model with a given prior, compared to the same dataset with a different model obtained from a previous fit, best fit to the other dataset. So you see the prior for this model are inspired by the fit to the other dataset. So it's a complicated way of saying that you follow the expectation of IceCube, for example, for the diffuse power law, and you see whether the two are in tension, trying to fit also ChemTreeNet. Now, of course, everything is super simple because you have only one event in a given in an energy bin where IceCube didn't see anything. So you focus on that energy bin and you compute ratios, for example, of the expectation for IceCube and the expectation for ChemTreeNet. So delta is IceCube expected over ChemTreeNet expected in the ultra high energy bin. Now, not surprisingly, this delta is super big, so it's of order 100. Okay, for obvious reason, which goes back to the volume and to the exposure of IceCube compared to ChemTreeNet. So there is a factor of 12 years compared to less than 1 year. So it's already a big factor that is difficult to reduce. So this is a way to show as a function of, for example, this slight energy dependent on the cross section, but as you see, these are straight line compared to lambda. But especially as a function of the index of the power law, what are the expectation fixing the best fit, the yellow for IceCube for ChemTreeNet, and you see that the ChemTreeNet is the is the dot dashed, and you see that in this energy, for the fit of IceCube, you should expect a very small fraction of events at ChemTreeNet. So if you compute the ratio delta, you see a factor of 70. So you should have seen 1/70 of an event at ChemTreeNet given IceCube, which is telling that there is a tension. Now, how big is the tension? So this is another way of comparing the two datasets, doing a fit to IceCube alone and to ChemTreeNet alone, and you see that with the same model they don't touch. Okay. So the bias factor for this defined in our sense, so prioritizing the best fit of IceCube and then comparing to the fit to ChemTreeNet without strong priors, you get a bias factor of 20, which is mild to strong tension according to Jeffrey. You know this book, Jeffrey's criterion. Okay. So power law has this tension with, I mean, if you try to translate this number to sigma, is slightly something like 3 sigma for the degree of freedom in play. Okay. What about, I think I have 5 minutes or something left, but it should be enough. What about point source? Now, apparently, I mean, when you think about point source, you think that it is better, but it actually worse. For the reason explained by this plot. So this plot shows 2 lines. One is red and one is yellow. I see it yellow. So one is ChemTreeNet, the red one, and the other is IceCube. And it is assuming the starting at 1 a.m. you have seen the event. Okay, on the 23rd of February 2023. Okay. So, and you reconstructed, so ChemTreeNet reconstructed the direction of this. So then, given the position, you can evolve it during the day. So we'll do it will do whatever it has to do. So the typical distance, the depth of the detector as compared to the incoming point on the surface of Earth as a function of time, knowing the initial location. And you see that KMT-net on average sees, so the average length of KMT-net is 3,000 kilometers, okay, because it covers most of the sky somehow. While IceCube is at the South Pole, so it is constant, of course, okay? And there is a huge separation between 15 kilometers, which is, the typical length traveled by the hypothetical neutrino at IceCube, compared to the average length traveled by the hypothetical neutrino at KMT-net, okay? So what does it mean, this plot? It means that most of time, the neutrino are attenuated at KMT-net, okay? So the attenuation of neutrino is more important for a point source with this reconstructed initial position than for a diffuse, okay? Another way of showing this is this plot, which these two, I didn't do this plot, but I like this plot. So, other people in our paper did it. So these are the average attenuation in the sky at IceCube and KMT-net. Okay, and you see that for the location of the event, KMT-net is more attenuated at the typical energies under consideration. So you see these red circles. This is the position of the source in galactic, the reconstructed direction of the neutrino in this galactic map. And okay, even without the plots, you can compute the ratio, and the ratio grows because half of time during the day there is a huge attenuation for the neutrino at KMT-net. So IceCube is not attenuated because it's just 15 kilometers. KMT-net is attenuated half of time because half of time the span is comparable to the Earth's radius. Okay, so you expect compatibly with these two plots an important attenuation. Anyway, so if you compute again the bias factor for a point source, maybe with energy localization, you might have two logical possible approaches. The first one is to say, okay, so this has nothing to do with the diffuse measured flux of neutrinos by IceCube, but again, I want to prioritize the fact that IceCube didn't see anything. But conversely, you can do the opposite. So you can also say, okay, whatever.
5 minutes left.
Yeah. Yes. So whatever. I mean, I want to prioritize KMT-net now. So I say, okay, KMT-net that measures something that defines the flux of neutrinos in that energy bin. And of course, these two, assumptions they give different tensions. And it's better to say that you were expecting the number of events predicted by IceCube somehow. So you want to prioritize IceCube because in one way the bias factor only grows linearly in this ratio, which is still pretty high. Otherwise, it grows quadratically. Okay. So you want to still say that you were extremely lucky with KMT-net. Otherwise, you have an even bigger tension. Okay, but maybe you are an optimist. You say KMT-net has defined one rate of event per year, one event per year at that energy, and that will screw up completely IceCube. But I think you still have the prior that IceCube has more information about this still. Because it's taking data for way longer time than K3net, that still you want to, have like a weight on the fact that ice cube have seen 0 in that energy bin for the past 12 years. Okay, so this is. Let me also mention that this statement that you see in this slide is slightly different from a previous paper, from another paper that appeared on February. So I think the point source is not the way to reduce the tension, unless you assume that this point source is transient in time. But that is okay. I don't know how to to make a robust statement about how can exist a transient source that reduces effectively the time exposure of ice cube as compared to K3net. Okay, let me recap these two possibilities with one table. So in this table, there are different models. For each model, I compute, so we computed the ratio of event in this ultra energy bin expected of ice cube as compared to K3net. And then when possible, I compute also the bias factor prioritizing both ice cube or K3net. And you see that the stronger tensions are when you say that K3net defines a flux of 1 event per year in that energy bin, while lesser tensions are found when you still prioritize the fact that ice cube didn't see anything. Okay, and the only way to reconcile in this bias sense the two data sets are assuming a transient, but which I don't know how to justify on astrophysics, because I don't know this subject anyway. So I think it makes sense to say that there is a slight tension. Probably as people in the collaboration are not really taking too seriously this tension. Maybe they have a better way of estimating this. But these results are consistent with what you might find in other papers. But I think I wanted to emphasize that the point source, for physical reasons that I try to explain, maybe it's not the best way to try to solve this issue and make the two data sets compatible. So other effects or BSM. So from the restricted direction, K3net is strongly attenuated. I mean, it's an accident. So it's an accident that for the same angle, ice cube only sees 15 kilometers of material, and the other sees thousands of kilometers during the day. So so eventually the ratio of event day average is even bigger for a point source, as I discussed. So the only way to tune away this unfortunate coincidence is to make K3net more transparent, or ice cube more attenuated. So we thought of trying to have a solution boosting the neutrino tau flux, because neutrino can be long-lived over 15 kilometers. Sorry, tau can be long-lived over 15 kilometers at these energies. But on the same scales where tau are long-lived, K3net is still attenuated. So the tau neutrinos have still to travel that much, and so they will be attenuated. So we didn't find a compelling case of maybe saying, okay, if you have a very strong flux of not democratic tau neutrinos at Earth, maybe this relieves the tension. But still, it's an effect that might be important even at lower energies. And the other possible solution along these lines is to have another particle which is neutron, doesn't lose energy, and it is unstable, so like a heavy tau. But again, it seems a bit contrived to proceed this way. So we didn't explore much this possibility. But of course, if in another 2 months ChemTreeNet sees another event, I mean, then you start also to consider these possibilities. So let me conclude. So the tension is there. Is at the level of mild to strong tension in bias sense, or 3 sigma something, if you want to quote sigmas. But the distribution are really Gaussian, so I don't know how to do a proper translation. So at the moment, only assuming that this was a transient phenomenon in the sky, then you might relieve the tension and not worry at all. Or so I think the only solution is just to say the blue sentence. So ChemTreeNet has seen another fluctuation, and it shouldn't see anything else in that bin for the next decades of exposure, unless IceCube starts to see something. For future work, I think we can improve our analysis. I would like to, include systematic uncertainties, not like just with yet another parameter, but can include like marginalizing over a possible distribution of, energy uncertainty in the cross section, density effects. So we didn't really exploit, maybe the unknown. The unknown density profile of Earth to maybe see whether this can bias a little bit favor ChemTreeNet over IceCube. So at order 0, also at first order, it does not. But maybe if one knows really the precisely density of Earth around ChemTreeNet, maybe there is some super dense material. I don't know. I'm just joking, but. Super dense region in the Mediterranean Sea, then you might improve the calculation. And in general, I think one can just systematize this by writing a code. Okay, even because ChemTreeNet is only just a fraction of the design experiment that is supposed to be. So in the future there will be for sure even more statistics, and so I think it's something that we might want to take with some attention for the future. And that's it. Thank you. Sorry, I was slightly over time.
Thank you for the nice talk. Any question from the audience? Please unmute yourself and ask.